Thank you very much for being here. And Peter started very nicely describing the topic that we are working in. So both looking at the anthropogenic sound noise and the animals that lives in the ocean. I will try to pick up some examples from this world, both in terms of measurements, but also then how measurements will affect, how the noise levels will affect animals. I had planned to talk about invertebrates, that means octopus, mussels and so on, but I couldn't find the time. I had so much else to talk about today, so I leave them out here. But invertebrates, they also have senses of senses for hearing or sensing vibrations, so they can actually be impacted by sound as well. So that's a topic for another presentation. So I'm going to just mention my co-authors Emilia Lalander and Robin Nordström Larsson, who has been doing a lot of the analysis behind these presentations. So it's very much a team effort. So when we are studying effects from noise on marine animals, we have to consider the animal's whole life history, because there will be different kind of impacts depending on where in the life cycle you are, but also what time of year and what are the animals do. So in this case, I take cod. They start as a small egg, becomes larvae, a juvenile, adult at 3-4 years old. They meet, they spawn, and then the circle starts all over again. So depending on where the noise gets into their life history, it will have effect on different ways. We have seen that noise can affect actually the survival of eggs. It can impact larvae, like Peter showed with the coral reef larvae, that they both need sound somehow to navigate, but in this case sound can also kill them or reduce their growth. Juveniles and adults can be affected in various ways that I will come to in a while. Because noise, as we see it today, have increased in the last couple of 100 years. And the animals were, in the evolutionary terms, is very recent the sound has come into their lives. So they are not adapted yet today to a more noise environment. This is very famous circles that came from a study from Richardson in 1995 describing what kind of effects can sound have on animals. If you go first as far as the circles out, when the sound is high enough, animals can detect it. After that, it becomes a little bit louder. It can mask the animal's own communication, or from the soundscape, keynote sounds from the environment they need to navigate, for example. If it becomes even more loud, it can trigger behavior reactions. It can cause physical injury, both to the hearing organs, but also internally if it's really loud enough. And at the end, close to a sound source like an explosion and so on, it can actually kill the animal, purely because of it's such a high energy output into the water. But how the animals will react depends on various things. Like I mentioned, the life history, but you also have the hearing ability, like Peter mentioned. Behavior and motivation. If an animal is very highly motivated to spawn, for example, then they can actually withstand higher sound noise levels than otherwise. But also the impact can change over year. Then when we try to study the impact, it's quite complex. But we need to have good information of the source. That means noise level, you have the duration, but also frequency. And then the sound will travel in the water column. And then you need to know a little bit about the transmission loss, as we say, how much energy is lost in the way. And that will depend on salinity. Bottom, a hard bottom will reflect the sound more than a mud sediment. It will just dampen the sound. And also how much sound is in the environment already. And then you have the receiver. So the impact, again, it will be depending on the anatomy, the hearing ability. Previous experience is actually something that's very important when you're studying fish, but also context. And we know we started maybe this science topic in the Second World War when we tried to look for submarines. That was kickstarting the technology. And I would say that we have more knowledge today about the technical part of this topic That means the sound, how to measure sound, source characteristics, but also sound propagation through models. So we have more information on this side than we have on the biology side about animals' hearing. For example, for fish, it's around 40,000 fish species out there. And they look different. They have different kind of hearing organs. I always bring this picture in. This is actually a small sand goby. It's 5 centimeter big fish. A PhD student took it to a dentist to see if it has a swim bladder, and it has a small swim bladder there. And here you see the inner ear, the otolith organs. It's stones that will measure vibration. One thing that we really lack information on, what is the impact on population? We can definitely say that it will impact an individual. We can measure that, we can see that. But how will that cascade up to a population level? That we have very few information on today. FY, we are maybe not the biggest on biology. I'm the only biologist in the department, so it's a lot of work. But we are better maybe in measuring. So here is 3 examples on studies. We have been out measuring sound, measuring particle motion, what Peter talked about, in collaboration with others. So we've been up to measuring sound with air guns. When they're looking for oil, it's an air gun that produces the sound. We had tagged cod in a huge net pen. Similar here up also in Norway, we had mackerel in a cage where we filmed, and then also an air gun passed. This is a study up in Älvkarleby where Swedish SLU, Svenska Lantbruksuniversitetet, tested bubble curtains as tried to scare fish not to swim to the water turbines to get fish meat. So we tried to play sound and also measure how much sound could get in there. So that's a little bit what I do with my colleagues, that we go out and experimentally test these kind of things. But we also go out and measure sound in the big ocean. What I will focus on this talk is the impact on masking. Peter mentioned that. And that is when there is sound out there that actually will impact your hearing ability or the ability to detect this signal. So we first have a sender there that produces a sound with a certain source level, and we have a receiver. And then you will reduce some of the noise through propagation. The receiver can hear it, but they also do certain things to actually gain, to amplify their hearing. But then the noise comes in, a ship in this case. It will be more difficult for the second fish to hear the first fish. And that is something we call signal-to-noise ratio. And that's very important also for us. Even though we know exactly where we hear, we need to have certain signal-to-noise ratio enabled to hear that sound. But we can do certain things to increase the probability of actually getting in contact. We can either raise our voice, like Peter said. We can also alter our behavior. We can turn our head so the ear is more closer to the sound. Or we can move closer in order to reduce the propagation loss between the sender and the receiver. These are key factors to actually determine if we can talk to each other or hear this kind of sound. But if you increase the background levels, for example with 20 decibels, which is quite a lot, then the communication range will reduce with 90%. So if we started at 100 meters away, I need to move up to 10 meters before I can understand what Peter is saying. We can remember these numbers in a while. But not all animals can respond in this manner. And that's very important because they were developed in a very different sea than we see today. I will briefly come into one example which is not far from here. We call it the Tango project. 1st of July this year, there was a rerouting of the major shipping lane in southern Kattegat. We have Kullen up here. So from until 1st of July, most ship got from Skagen up here down, turn left into Öresund. But after 1st of July, more vessels was shipped over here, close to the Swedish border. So we, together with Naturhistoriska Riksmuseet, Julia, financed by Trafikverket, Transportstyrelsen and Swedish Agency of Marine and Water Management, got some funds to measure 1 year before the shipping lane and 1 year after. what is the impact on the soundscape and on the harbor porpoise. So this area in southern Kattegat is very important for cod. This red area is no fishing allowed, and it's also a major spawning area. And also very recently it was announced to be a natural reserve by Skåne's county administration. And I just put an arrow in here. The new shipping lane, the route S, goes straight through. They know about it, but it's more important to change the shipping route because the shipping lane was full. There was risk of collision, oil spills and no sowing. In this case, nature came second. Sound is very important for fish, and especially cod. If you can play that sound, please. That's actually a cod grunting. It has muscles around its swim bladder to produce this kind of grunting sound. We can see it here. These pulses that goes, and they can only just one, it's called a knock, or this a pulse train, then called a grunt. They do this, among other things, when they are spawning. The male, the bigger male, the more sound it makes, attracts the female and do a very intricate dance before they started to mate, to spawn. So sound for them is very important. And I will show you later on how much sound has the level increased in their prime spawning area due to this shipping lane. We saw already, this is preliminary results now, this is just came in. So this is a picture of just the ship traffic, because all ships of larger size has a radio beacon that we can gather all that information. And then we plot the map on where they go. So the more the red, the more ship it is. So here is in last week in June, before the shipping lane came. So this is a major ship route. Here, there are still ships going here, but not to the same extent as 1 week later. You see the red lines here is very, very red. So we have measurement stations up here and also outside Kullen. But we just got data from these ones now. Our hydrophones out here is still in the ocean, so we're going to pick them up in December. And we can also show in more detail that much more ship moved as planned into the eastern shipping route. So looking at the weeks here, this is May. Yes, May, June is 1st of July. And this number of ships, passengers per 6 hours in the easternly, the S route. So up here, it started to turn, so we got much more up here. It went from 3 to 8 ships per 6 hours. And same, we saw a reduction, roughly the same scale, in the westerly route, the route T. So from 15 to 9 ships per 6 hours, as we expected. But what was this impact on the soundscape? This has almost never been shown in the sea before, so we are really happy with this kind of data coming in. You can do it in 2 ways, present data. You can go at the measure, you get point measurements, but you can also model with the use of these radio beacons. So here's actually sound maps of the whole region. I won't go into details, but this shows at least that this is the week before, so there's not much happening on this side here. But suddenly we started to see some more red coming in here. So it's more sound in this part here. Unfortunately, this was just for the week after. When we saw on the ship traffic, it increased even more the following week, but we don't have that map yet. But this is a clear indication that the shipping lane change affects the sound in the whole southern region. Coming to data, which I would like to show you, is that if we're looking at certain frequency bands, because cod has more of a narrow hearing than many other animals. They hear from maybe a few hertz up to 400 hertz. That's their hearing range. So we pick up one of those frequency bands, 125 hertz, because very good for them. A lot of energy from the ships, but also high impact on the cod. And we see that it shows the same pattern as the shipping lane. So here is before, and suddenly it goes up 5 dB approximately. And then it continues. This is data from 2 stations up there outside Falkenberg. But we also have broadband data. We integrate energy over a larger. It's from 10 hertz up to 20 kilohertz. And then it's roughly the same, 4 decibels And for you who live in an air acoustic world, going from 94 to 98 decibel, maybe it's not that much, but it's fairly loud levels. We are 1 and 3 kilometers away from the shipping lane where they go. You can play this sound here. This is what Peter talked about before. This is cavitation, this sparkling like you're frying a pan with bacon. This is the bubbles collapsing, creating these sparks of noise, which can be very loud. So what's happening now to our communication range? Not 5 minutes yet, no? Yeah, thank you. So before in the old shipping lane, of course there were sounds, but we could communicate at 100 meters distance. Then the ship comes in, and for easiest way, I say it was an increase by 6, but it was 4 to 5. But again, this is just really rough numbers. So what will happen then is that actually the communication distance will be half. So suddenly, all fish will have to reduce their distance by 50% in order to have the same communication range as before. And we also saw the number of vessels. It was almost 8 per 6 hours, which I think will increase even more. But we can detect in our hydrophones a ship that is more than 10 kilometers away. So having 1-2 ships per hour, that means you will have a constant sound, a constant noise in the water from the ships. Other areas with much more traffic, like Julia is going to talk about, there we have maybe 4 or 5 ships per hour, which means that we cannot almost detect any natural sounds at all anymore. Just in the higher frequency bands where ship energy doesn't go. So to summarize a little bit, is that the animals that live in the water now, they were developed in a much different sea than before. And they have not had a chance to adapt to the new sound regime that we see today. And most of them probably won't be able to adapt because they are locked in their niche where they have found from thousands of years ago. But we don't know. We are quite good at the research on source characteristics and level, but we need more because new sources comes in. I was just out a few weeks ago measuring noise from water scooters, because that's been quite a big thing in summer in Sweden, a lot of water scooters coming around. So we measure sound from them to see what is the source characteristics. But then on the biology side, we need to identify more on the life history of the animals. Where is the impact? Where is the challenge? And where is the bottleneck? Because we have high mortality at certain life stages. Going from egg to larvae, I think we lose maybe for cod 90%. And then from larvae to juvenile, we lose another 90%. So we need to know where are the bottlenecks. And also link impact on population effects. Managers today, they are aware of this. Underwater sound is not the #1 killing for underwater for fish. That is commercial fishing and eutrophication and so on. But it is there. It's one of those that increase the likelihood that animals will be affected. So they need to have it in their management plan, in their marine special planning, and also when we're doing impact assessments for new activities like piling, for example. And with that, I would like to say thank you. Showing one of my favorite animals, vingsnäcka in Swedish, a small nice snail swimming around in the sea. Thank you.